Hi friends, today let us discuss about finite state machine. We'll be discussing the first type of machine, that is finite state machine, which accepts regular languages. As set in the hierarchy, finite state machine accepts the regular languages, which are defined by the regular grammar, also represented in the form of regular expression. Finite state machine is a computational device having a string as input and having one of two possible outputs, accept or reject. It is also known as finite state automata. Let us discuss how to design a finite state machine. Finite state machine starts with an initial state, also known as start state, represented by a circle with an inward arrow into it. This state can be labeled with any uppercase or lowercase or any symbols. Every FSM will be having one and only one initial state or the start state into it. The final state or accepting state is represented by double circle. So you can see here two circles and the state is labeled as Q1. So this represents that the state is final state or accepting states. And here you may have one or more number of states marked as final states, but minimum one state must be there in the finite state machine to check whether the given string is accepted or rejected. A state which is neither initial nor accepting state is called as intermediate state. For example, in this small FSM, Q0 is the initial state, Q2 is the final state, Q1 is an intermediate state. And from Q0 state for input A, it is going to Q1. Again, from Q1 for input A, it is going to Q2. So, till now we discussed how to represent initial state, start state, final state or accepting state, intermediate state, a path from one state to another state through a input symbol represented by summation. Input string is fed to the finite state machine one symbol at a time from left to right. Each time it receives a symbol considering the current state and the new symbol going to the next state. For example, current state is Q0. For the new symbol A, it is going to the next state, that is Q1. Similarly, current state is Q1. For the new symbol A, it is going to the next state Q2. And if the machine runs out of the input and is at the accepting state, then the string is accepted, else it is rejected.
Let us see how to design some simple finite state machines. For example, assume summation is A, that is, the alphabet summation consists of only one symbol, that is A, and the language to be generated consists of only one string, that is epsilon. Then the finite state machine for this language is represented as initial state itself is the final state. So, if we represent initial state as the final state, then the string obtained is epsilon.
In this example, the language contains only one string of length 1, that is A. To design a FSM of string length 1, we need two states, Q0 and Q1, where Q0 for one compulsory transition for input symbol A reaches final state Q1. So this is the FSM for the language containing a string A. Let us consider a language consisting a string of length 2. FSM for a string of length 2 needs three states, Q0, Q1 and Q2, where from Q0 for a compulsory A reaches Q1, and again from Q1 for the second compulsory A going to the final state. So from the start state Q0 for input string A, it reaches the final state Q2. Hence string AA belongs to this particular finite state machine. In this example, we have combined both example 2 and example 3. That is, this language contains two strings A, AA. It means if I have a single A, then the finite state must accept that string, and if I have AA, then also the finite state must accept the string. The finite state obtained for this language is, so for a single A, initial state Q0 for one compulsory A input reaching to Q1. As A must be accepted, Q1 will be the final state. And along with A, even AA also must be accepted. So from Q0, for one A it has reached Q1. Again from Q1 for one more compulsory A it reaches Q2, which is the final state. So hence both the strings A reaches the final state, A reaches the final state. You can see here we have discussed every finite state has one single start state and it can have one or more number of final states. This is an example wherein you have more than one final states. Example 5, summation A, and the language contains 0 or more number of A's. 0 or more number of A's means L containing 0 A's, 1 A's, 2 A's, 3 A's, 4 A's and so on. 0 A's, it means epsilon, 1A, 2A, 3A and so on. If we represent this language, the language can also be stated as A raised to n, where n is greater than or equal to 0. If n is equal to 0, epsilon. If n is equal to 1, 1a. If n is equal to 2, 2a's and so on. So the finite state obtained for this language is, as we have already seen in example 1, how do you represent epsilon? Epsilon epsilon is represented as initial state Q0 itself as final state representing epsilon. Now, if I want one single A, then I'll take a self loop to the same state Q0. Start state Q0, taking one self loop for one single A reaches Q0, which is the final state, hence the string is accepted. Similarly for 3 A's, start from Q0 initial state, 1A, 2A, 3A reaches state Q0, which is a final state, hence the string is accepted by this particular finite state machine. Let us take next example. A language consisting of even number of A's, that is 0 A's, 2 A's, 4 A's and so on. The language can also be represented as a raised to 2n, where n is greater than or equal to 0. Since the first string is epsilon, as you know, just now we have discussed, initial state will be the final state. So this FSM will accept the epsilon string. Next, coming to string AA. 1, if we come across 1A, then it must not be accepted. But if we come across 2 A's, then the string must be accepted. So how do we design this? So initial state is a final state. We have one compulsory transition for input A going to state Q1. Then the string must not be accepted. So the state Q1 is an intermediate state. But as you know, the second A must be accepted. So at that time what to do is take one more transition from Q1 for input symbol A back to Q0, which is a final state. Now if you see, string AA start from the initial state Q0, 1A going to Q1 and second A going to Q0, which is a final state. Hence the string AA is accepted. Similarly, let us take one more string, 4A's. Start with initial state Q0. First A from Q0 it is going to Q1. Second A it is going to Q0. Third A to Q1 and fourth A back to Q0. And here Q0 is the final state as the string is accepted. The logic here is when you have one odd number of A's, then you will be in the intermediate states. When you come across even number of A's, you will be in the final state. So this is the finite state machine for the language consisting of even number of A's. Similarly, if I go for defining a language having odd number of A's, then how do you design finite state machine? Odd number of A's possible strings in the language are 1A, 3A's, 5A's and so on. At that time, can initial state be the final state? No, because epsilon is not the string in this language. So first we must have one compulsory A reaching the final state. So we have already designed initial state Q0 for one compulsory A going to state Q1, which is the final state. So by this FSM, first string is accepted, that is one single A. What about 3 A's? For that, what we have to do? 1A reaches the final state. Second A will go to the intermediate state, that is Q0, and third A it will go back to state Q1. So the same logic is applied here. When you have odd number of A's, it will go from intermediate to final. When you have even number of A's, it will come from final to intermediate. So finally, to reach the final state, you must come across odd number of A's. So this is a finite state machine designed for the language consisting of odd number of A's. Till now, we have discussed with only one symbol. Now, let us take some more examples wherein the alphabet consists of more than one symbol. So, in this example, we have A and B, two symbols in the alphabet, and the language containing either A or a B as its string. Then, how do we design a finite state machine? It is very simple. From initial state, one compulsory transition to A, with A reaching the final state, or from the initial state, one compulsory transition B to state Q1, which is the final state. This can also be represented as with one single transition having comma in between. This is equivalent to this finite state machine, either A or B, A or B. So both these finite state machines are equivalent. We have discussed a language consisting of even number of A's. We'll take one more language which is similar to it but consisting of two symbols in the alphabet A and B. The language consists of all possible strings where the string length is even. It means it can be either A or B, but the string length must be even. Possible strings in this language are: no occurrence of A or B represents epsilon. Two A's, string length is even. AB or BA, string length is 2. BB, string length is 2. AAAA, string length is 4. So similarly, it can be either A or B, but string length must be even. So how we design the finite state machine for this? First we have epsilon, so by default initial state is the final state. And what was the logic applied? If I come across one symbol, then it will be in the intermediate state. If I go for the second symbol, then it must reach the final state. So same logic is applied here. When I come across a or a B, it will go to intermediate state. When I come across another A or B, that is string length is 2, it will go back into the loop to Q0, which is the final state. So let us take up one example, AB. AB is a string which belongs to this particular language. Start with initial state Q0, A reaches Q1, for B it will reach Q0, which is the final state as the string is accepted. Similarly, let us see how to design a FSM for the language containing all possible strings of odd length. Possible strings in this language are A, B of length 1, then string of combination of A and B of length 3, of length 5, and so on. Here also the same logic is applied. Start with an initial state Q0. For one input symbol A or B, it reaches the final state. That is, for odd number of A's or B's, it will be in the final state. When it comes across even string length, it will be back into the intermediate state. Let us take an example of string A B B B A. So this is string of length 5 and this must be accepted by this particular FSM. Start with initial state Q0. For A, reach Q1, B, B, B and last A, it reaches the final state. Input string is consumed. It has reached the final state Q1. Hence, the string is accepted. So these are some simple finite state machines which we have designed. We'll see few more finite state machines in the next lecture. FSM is applicable in many of the domains. To name a few, it is used in vending machines, traffic lights, video games, text parsing, CPU controllers, protocol analysis, natural language processing, speech recognition, etc. Examples of these applications will be studying in detail in the future lectures. Finite state machine is of two types: deterministic finite state machine and non-deterministic finite state machine. In the next lecture, we'll be discussing these different types of finite state machine. Thank you.